Okay, so as I told you, the plan for today is like I'll probably just mention some brief things in the next 30, 40 minutes, and then I'll be done. And then if you want to stay here and just to ask me questions about the exam, you can do so. But yeah, I'll try to keep it short, just to mention some things, emphasize some of the stuff that I said last week involving a Taylor series, but I don't want to start anything new material like for the final 2 days. So it would just will still be relevant for what we're going to talk about doing on the exam. So oh, okay, so one thing useful to know, which I think you saw in the workshop from last week, is that you can use like a Taylor series sometimes to as an alternative to L'Hopital's theorem, which is nice to know. Like it's not, doesn't change that much, but it's kind of like good to know that there's like another application that they have. So another application of a Taylor series um is that they can be used to find limits, yes.
Lecture 19 was last.
Oh, was it?
Yeah.
Oh, okay.
Yeah.
Huh, thank you. Like, okay, I was double check. I don't know why. Like, I'll have to go through my PDFs, but thanks for letting me know. What do I have here on my iPad? Oh, okay, so this is totally off. Like, I'll check all those numbers then because yeah, I don't know what I did wrong. So they can be used to find limits. So I'll just give you like a quick example because so as an alternative to L'Hopital's theorem to using L'Hopital. Oh, I think I'm missing an S. Um, so this is like a limit from Calc 1. It's one of the first limits involving trigonometric functions that you study, something like cosine of x minus 1 over x squared. Oops, I didn't put the x. So cosine of x minus 1 over x squared. Okay. So in fact, it's one of the very first ones. So you don't even need L'Hopital's theorem to prove it because this is what is needed. The thing is like L'Hopital's can become a bit circular because to use L'Hopital, you need to know the derivatives, right? But to find the derivatives of like a cosine or a sine, you need to know these limits ahead of time, right? So you cannot like, in principle, you actually do need to have like a way to find them on their own. But just to remind you how this would have gone if you know L'Hopital's rule, because this is like a limit of the form 0/0, right? So according to L'Hopital, you would have taken, I'll just put LH to say that I'm using L'Hopital's rule. You take the ratio of the derivative, so it becomes negative sine of x divided by 2x, and that is still 0/0. So you do L'Hopital one more time. And so the derivative of sine is cosine, so you get negative cosine of x over 2. And this is great because now this is ready to be evaluated using L'Hopital, just like by simple plugging. So cosine of 0 is 1, so you get negative 1/2. Okay, so that is what the limit would have given you. Um, from the Taylor series perspective, Which again is just like useful to understand that you can do that. Not necessarily that it's more practical in like, in terms of time consuming, but like from the perspective of a Taylor series, what you do is expand the cosine at the power series. So use like the Taylor expansion. So an alternative way to find this is by using the power series of expansion of cosine of x by using I mean like the Taylor series. Taylor series. And again, this is one of the four that you need to know. So you need to know the cosine one, sine, e to the x, and the geometric one, like 1/1 minus x. Those are the four that are like the only four ones that I'm expecting to you to know. But so cosine of x is it's even, so that helps you to like it helps you remember that it should only be even powers of x because cosine is even, so you get. And then well, I'll put the 2n factorial here, and then there's like a -1 to the n, so this goes from 0 to infinity. So just whenever you write like a Taylor series, it's always useful to at least evaluate at the first three terms of the series just to have like a sense of how things are starting to look like. So this is 1 minus x squared over 2. And then the next one will be a plus, so plus x to the 4, and 2 times 2 is 4. 4 factorial, 4 times 3 times 2, that is 24. Dot, 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 dot. So that goes on forever, but it's always, again, whenever you have a Taylor series, like a good rule of thumb is always plug in the first three terms to see what you're dealing with. That making sense? And then I will substitute this into the limit. So when you're looking at the limit, then you get the limit as x goes to 0 of cosine of x, but cosine of x, I'll put the dots in a slightly more precise way. So I'll write these three terms first, and then what is left in the series, like I mean the remaining terms, it starts with n equals 3. So you get. So here I evaluated, so this was actually, I can be more precise here. This was n equals 0. This is what you get if you put n equals 1, and this is what you get if you put n equals 2. So the remaining terms in the series start at n equals 3 because I did the first three evaluations explicitly. So that is what you have instead of cosine of x now. You're subtracting 1 from it. And then you are dividing by x squared. So when like there's some simplifications which happen now because there's a 1 here and a 1 here, so they cancel. Well, I'll just copy paste this. Oops. It's a parenthesis, yeah. Yeah. So it's -1 to the end. I mean, there are other ways to write it. Like the important thing is that it has to alternate, like plus minus, plus minus, plus minus, so like that's the easiest way to write it down. Okay, and then kind of what you notice is that everything in these terms will have at least a power of x squared, right? Because this has like an x squared, x to the 4. This is like x to the 6, x to the 8, x to the 10, all times some other numbers, right? Like that doesn't matter too much. So like what I'm saying is that there's kind of like an x squared that you could factor out to simplify this. So this would give you the limit as x goes to 0 of negative. So there's no more fractions, right? Like the denominator goes away because you can cancel it. So the only way, like the way to say that you kind of like factor it out is like you just drop the exponent by 2. So I'll put it like x to the 2n minus 2 over 2n factorial. And then, which is something nice of the Taylor series expanded perspective, because it gives you more information about how the numbers are behaving as you get towards 0. So if you use L'Hopital, right? If you use L'Hopital's rule, yeah, you just get -1/2, but you don't know as you get closer to 0 how close you are to -1/2. This gives you like a more precise understanding of how much you deviate from the limit, because this is saying that the answer is -1/2 plus x squared over 24 plus all this other stuff. So it tells you like, it does give you more like information of what you might call like an error term of how far away you are from the limit. The important thing here is that as x goes to 0, this will go to 0 because it has like a power of x, and all of these also have powers of x, so they don't contribute in the limit. So in the limit, all of this goes away, and then you just get to -1/2, which is like the same thing as before. So because like, all of these disappear, all of these become 0 in the limit. So it may not necessarily look like a shorter calculation, but it is like a more informative one. If again, you wanted to understand a bit better of how the limit is approaching its value, for like small values of x. Yeah. Oh, because the thing is that, I had an x squared, right? There was an x squared here. It had to kind of like cancel every term. So, this x squared, like, okay, let's see. So, let's start here because, okay, this x squared with this x squared, that just gives you like the -1/2, right? This x to the 4 with this x squared gives you x squared, right? But then x to the, maybe I should put it like here, x to the 2n divided by x squared, right? Is x to the 2n minus 2. So yes, from here, explanation. Yeah, no, sure. So right. So I kind of like did it like term by term, basically. Well, because that's the thing. Individually, n starts at 3, right? So if you put 3 here, you get 2 times 3, which is 6. 6 minus 2 is 4. So every term here is like at least has an x, right? So it's more than that. It's x to the 4, x to the 6, x to the 8. So they will have all powers of x. So like, yeah, I should also add that as a clarification. This is at least, since we have n equals 3, this is at least the smallest it will be is x to the 4. So it will be x to the 4x, of course, with the coefficients or not, but it will be x to the 4, x to the 6, x to the 8, x to the 10 for eternity. It keeps increasing. But the cool thing is that, like the important thing is that everything has at least a power of x. So, that's what makes it work that way. That makes sense. Okay, so the other thing is, which I have been using implicitly, but I don't think I've brought it up, like say it out loud. But another important thing to notice is that the moment you express a function as a power series, that essentially is the Taylor series of the function. So like, in a sense, there's only one Taylor series for a function. So what I mean, sometimes it is called like the uniqueness of the Taylor series. So meaning that if you have a function and you can write it as a power series on some interval of convergence, right? Because remember, like a power series, usually it only makes sense on an interval. If you have a function f of x, which you can express as a power series on some interval. Well, usually I have been centering things at the origin. So I'll just say that x is between negative r to r. So think of r as kind of like this radius of convergence. So here r is like this in radius of convergence. Oh, let me write n actually. So if you manage to write the function as a power series, then those coefficients are exactly the coefficients from the Taylor formula. So there's no like there are no two power series which would produce like the same function. Like then like the terms, then the constants or the coefficients. Like let me call them coefficients better. Are precisely those from Taylor's formula. Meaning that like Cn, what it would be is like the nth derivative at the origin at x equals 0 divided by n factorial, right? Which is why sometimes when the way to think about a Taylor series, it is just like it is a specific power series. It is nothing but a power series, but kind of like adapted to a function. That's kind of like you should think about it. Like the Taylor series goes hand in hand with the function, um, at least within on some interval of convergence. And so let me do an example of what I mean by this. So for example, if, and this is what I called last time, like that you parasitize on previous series. So like imagine like let's say that I wanted to find a Taylor series for cosine of root of x. Okay, so find a Taylor series cosine of root of x. So option one, which is tedious option, is find a formula for all the derivatives of this function, right? So it is kind of like the one that you don't want to try at home, right? So like if you put cosine of root of x, like option one, which is super long, so you won't use, um, is that you would like to find like a formula, find f prime of 0, f double prime of 0, f triple prime of 0, dot dot dot. Like you find a formula for the nth derivative, right? Evaluate at the origin, and once you have those numbers, you can cook up the Taylor series, right? Like using that formula. Option two, which is how I found some Taylor series last time, is that you kind of like start from a given Taylor series and you just kind of like massage it into the one that you care about. Sometimes it is less confusing if you use different variables for the letters, because otherwise it can be a bit like, all over the place. Once you have some practice, like you don't have to do that. But so let's call that option one. Option two, which is faster, is that you start from a known power series, or like start from a known Taylor series. Start from a like, well, let's call it Taylor series. So for example, this one, like if involves a cosine, so I would take the Taylor series for cosine, but I'll call it cosine of t instead of cosine of x, so that there's not like a misgiving of what I'm talking about. So the Taylor series for cosine of t is the one that I just wrote before, right? But now with t instead of like x. Oops, like, yeah, let's like, it can take some time. Okay, t to the 2n, right? And then in this case, it's just like a simple substitution. You think of t, again, for something like cosine, there's no restriction of what t can take, which values t can take, like the power, the integral of convergence is like all the real numbers. So t can be, is valid, this formula is valid for any t. So this is valid for t from negative infinity to infinity, So no restrictions, that's what I mean. Um, So in particular, since there are no restrictions, there's nothing preventing you of thinking, well, what if you take t as root of x for some other number x, So you write, so then you express t as root of x, and that immediately, almost like by just a substitution, you just get like an formula in terms of a power series for cosine of root of x. Well, of course, like here, like x has to be non-negative. For this to even make sense. Although at the end of the course, right, we'll talk about imaginary numbers, and we will take square roots of like negative numbers, but right now, like, we're still not doing that. Well, actually, let me just like write in green just to make clear where the substitution is happening. So you still had so the square cancels the square cancels the square root. So you just get x to the n. So the Taylor series for cosine of root of x would be negative 1 to the n of 2n factorial of x to the n. Oh, let me continue writing the last term in black. So just to show you what the change was. And that is essential, like what I'm trying to say, like what you this uniqueness business of the Taylor series says is that this is literally the same formula that you would have found if you had used like the formula, this will coincide, this agrees with what you would have obtained if you had used this formula for the Taylor series of the function. Okay. So because there are no different Taylor series that produces like that work for the same function. And so kind of like as a plus of this like approach, you kind of like get for free, you get for free like a formula for the nth derivative. Yes. Yes. Mhm. Right. Oh yeah. So for example, okay, so yes, if you had to, I actually think we had done something. Okay, right. I have it in a previous class lecture, right? But like yes, like you know, one of the we had found we had, let's see, like well actually I would do um I'm about to answer your question after I just finished what I was going to say here. Like the only thing that I wanted to say here is that because they're supposed to be the same, you get for free a formula for the nth derivative of the function at zero for what it's worth. So that's kind of like nice to so comparing terms, comparing the coefficients in front of x to the n, coefficients you get for free, that this is a coefficient in front of x to the n, and this is a coefficient in front of x to the n. So you get for free that -1 to the n over 2n factorial is the nth derivative of this function at 0 divided by n factorial. So that gives you like a formula for what the nth derivative at 0 would have been. So you get that -1 to the n times n factorial over 2n factorial is fn of 0. Which is way faster, actually, a way to find the formula for the nth derivative of the function if for whatever reason you wanted it. You know what I mean? Um, I think someone else had raised their hands before I answered this question about like the word can you do the plugin? Is anyone else? Yes.
Oh, the question was for the Taylor series. Um. This one is a power series and a Taylor series.
Right.
But the other one is just the Taylor series.
Well, I mean, that's what I was trying to say. The thing is like a Taylor series is always a power series. It's just that kind of like you think of them as like attached to a particular function, right? So you can totally call a Taylor series a power series. It's just that when you have all that I'm saying is that if I have like a random, like again, like if I have like a random power series, like for example, like this, let's say it starts at 1, right? Here I'm not necessarily thinking of a particular function, right? And that's why I'm only referring to it as a power series. But it could be, and I don't know, I would have to double think whether this one it is. It could be that these coefficients pop out as the derivatives, of a function, like the nth derivative of a function divided by n factorial and all this stuff. And if it happens to be the case, then you would also then call this a Taylor series, right? So, but you only call it like a Taylor series when it has like this extra condition that it kind of like have like a function you can associate to it. But a Taylor series being a power series, everything of a power series applies to the Taylor series because it's just like a specific power series. So in a sense, if you have like the world of power series, right? I'm saying kind of like there's this island of the Taylor series, which are kind of more special, because here you do have like kind of like a function that you're thinking about. Yes. Yes. or,
That we have right here.
uh-huh.
I know that if we did do the Taylor series for this function, it would, so that it's centered at zero.
Right.
To tell that it's centered at zero by looking at that power series.
You can, because it always, like, if it had been centered at one, it would then read x minus one to the end. So if it's, and 99% of the examples, I will always just center them at zero, because like nothing changes like conceptually. But right, it is easy to kind of like read off the center, because yeah, if it's like center at any other number, it says x minus a to the end. So like you would see like some number being subtracted from the variable x explicitly, if that makes sense. Is that making sense before I just go to answer like this other question about like the substitution? So yes, and that's actually a good other case. So right, like this trick has limitations on the domain. So for example, so let me just put this like as a comment here, like some limits of the trick. So if you remember, and also it's a good reminder, because this is like a very important power series. Like, I had the geometric series. If you remember like the formula for the geometric series, like, like the natural one, like you get that 1 minus x. 1 divided by 1 minus x is this thing. That's what the geometric series says. But this only works, if x is between -1 and 1. Okay. But right, like you could, and this is how I think I mentioned like before, like you could try to find like a Taylor expansion for ln, right? Because then if you integrate both sides of the equation, well, so this would give you ln of 1 minus x, I guess -1, but because of this chain rule business. So so for example here, because I do have this restriction, right, on x, I cannot come out of the blue and say, oh, let's take x, so here you cannot, you can't use this to find. Well, I'll use a different letter again, just because like it could be inconvenient if I call everything x, but you could not use this to find, like, for example, what, let's say something that is like obviously, outside the, like one, like the Taylor series. Let's say what would be, like, for example, think of x as, well, no, that would be silly. Like, think of, I mean, right, like, or let's say that I wanted to think of x as being t plus 3, right? Then if I took x to be 3, t plus 3, then what is 1 minus x? It would be 1 minus t plus 3. So that would give you minus t minus 2. Well, so let me just put t minus 3 here, so that I don't want to work with a bunch of negative numbers everywhere. So that becomes 4 minus t. Right. So if I had asked you to find ln of 4 minus t, right? For whatever reason, then you can use that, provided, the t kind of like satisfies like the corresponding inequalities under these restrictions, right? Like, so for example, what would that give you? Like, this would be a Taylor series. What is x? X is now t minus 3, right? So it becomes t minus 3, which, by the way, automatically centers it at 3, right? Because now you're subtracting 3 from the variable. So it kind of becomes, which makes sense, because if you shift the variable, you're kind of moving where like the origin was located. So it would make sense like the center. Yes.
So when we integrate, what is it become x to the n plus 1?
Oh, yeah, no. Like, what did I do here? Oops. Yeah. Okay, this was a terrible integration. No, you're good. Okay, you should have gelled at me. Okay, so okay, good. Perfect. So then this becomes a n plus one, right? Oh, and there was a minus here. So like let's say the minus ln of 4 minus t, n plus one over n plus one, perfect. But right, like of course, like this formula would only have that been valid for whatever like the inequality in terms of t is. So this would have been valid for minus one less than t minus three less than one. And so if you solve for t, that gives you what? Two uh, greater than t, that t is between 2 and 4. So like anything else, like this would not have been like this would if for whatever reason you had wanted to find it somewhere else, like you have to kind of like at least you cannot parasitize something particular Taylor series. You either have to find it from scratch or like do something else. Okay. But when it's kind of nice, like e to the x, sine of x, cosine of x, it's almost like a free for all because you can plug in anything inside there. So you don't have to worry about like these restrictions because you have like minus infinity to infinity in the inequality bound. So like uh there's no place to add. Okay, so I think this like okay, I'm almost done. Just so this is kind of like some cute applications about Taylor's series that I wanted to mention. Just before we're just like as a motivation for what will come next, and also just like for future references. So oh my god, where is so many things that I have here? Okay, yes. Ah, let me see. Okay, so like I'll just show you a little bit of this stuff about the Fourier series, just so that you know that there's more out there. Okay, so we have been talking about this Taylor series. Let me see. Oh, here it is. Okay, so we have been talking about like a Taylor series, and when I told you about a Taylor series, is that a Taylor series is kind of like an approximation of the function. Well, a Taylor polynomial is an approximation of the function, use using like polynomials, and then the Taylor series is kind of like the limit of that. So but there are other ways to approximate functions which are convenient. So the picture is not super clear here. So let me draw it on the board. So, other ways to approximate functions which are convenient. Uh, One of them which are really useful is called like the Fourier series. So the Fourier series usually works better. It's a particular type of series. That's why it's called like a series. But it works better when you have like a periodic function. So a periodic function, as you may remember, like cosine and sine are just functions who repeat themselves after a while. So there are tricks to produce a periodic function. Like for example, you can take something like y equals x, which is definitely not periodic, right? But then you stop it somewhere and then you just clone it. So just keep part of the graph and then you kind of like repeat it like for eternity. So I artificially made it periodic, right? Just by cutting it and then copy paste, copy paste, copy paste. So that makes it like a periodic function. I think this is not the one that I was looking at. Ah, here it is, y equals x. Yeah, now it does look better, right? So this is kind of like this repeating pattern. And then there's like a Fourier series for it, which means because what are functions that you know which are periodic? Sines and cosines. So like what the Fourier series says is that you can express the function, this repeated pattern in terms of sines and cosines. So like, I mean, this is like the formula for it if you were interested, but like, it's kind of like cool to just see like what happens if you include more and more terms with the expansion. So here, like they're just like adding the first term. When you put n equals 1, you just have a sign, but then if you keep adding things, you'll see like the sum of more and more signs. So you see, do you see like, okay, so this is like being obtained by adding all those, like, put n equals 1, n equals 2, n equals 3, n equals 4, n equals 4, 5, and keep adding those things. Like, so this is like corresponds to a bunch of sines and cosines. Well, in this case, you only need sines because this is kind of like an odd function, so sines odd, so like, you only needed sines. But then there's a kind of like approximation in terms of sines and cosines. Okay. And that one of the reasons, okay, so which is kind of cool to know. One of the reasons that's useful, like, let me see if I can show you this here. So one of the reasons that's useful is that's what is used like with signal analysis. So for example, you can take, I don't know if like, let me see if I can center this like on the middle. So you can take like a signal, like the one that we were talking about, and you decompose it in terms of like the signs. Okay, so this vertical bar kind of like tells you how much like the coefficients, how big the coefficients are in the Taylor's in the Fourier series expansion. So, okay, this should make a small sound, hopefully not too bad. Okay, and then you can kind of like, so this is how like this sound wave sound. Then you can kind of control the modes of the Fourier series just by changing these coefficients. So let's see. And then like, and that is naturally what is used in signal analysis because maybe, you know, like the human ear cannot hear past certain frequencies. So you want to, if you're transmitting some data, you don't care about the frequencies that you cannot listen to. So you kind of like set on this coefficient equal to 0 because that's an easy way to compress a message, you see. And there's so many things you can do once like you have a decomposition in terms of sines and cosines. But you know, it's kind of like cool to see how you play out, you kind of like deform the signal just by changing the coefficients in the Fourier series. Okay, so, but it is really, it's actually related to the Taylor series, but for that you need to know complex numbers. So maybe at the end of the course, I can tell you what the relationship is, but let's end. Okay, so I'll stop here. And then as I was saying, I'll stay around in case you just want to ask me questions about the exam or whatever.